All right. Good afternoon, everyone. I'm happy to be back at JSAC this year to present our latest investigation about the APT we named PlushDaemon, and one of its most recent cyber espionage operations. For those who don't know me, my name is Facundo Munoz, and I am a researcher at ESET since 2021. I focus on China-aligned APTs, hunting for new groups, and reversing malware. This is my second time in this conference, and I would like to thank the organization and the speakers for their amazing work. For today's agenda, I will talk a little bit.
さて本日のアジェンダです。まず中国関連のアドバーサリー・イン・ザ・ミドル AIT
Introduction to PlushDaemon and the supply chain compromise of IPNE, and then we will go into the technical part of the presentation, where I will give some details about the slow stepper implant used by PlushDaemon, and to close, of course, I will talk about PlushDaemon capability for adversary in the middle. So, the China-aligned adversary in the middle club. Last year, I presented about the APT we named Black Boot. Their main initial access technique is to hijack updates from legitimate applications to install their malware in targeted machines. And I also introduced other APTs that we are tracking and that have the same capabilities. Liu Yu, which was presented by the guys from Team T5 in 2022, and as I mentioned before, Blackwood by me in 2024. I also introduced the Wizards APT, a group that targets gambling companies and individuals, and use a tool that we name Spellbinder that can redirect traffic in a network to hijack updates. And in 2023, we also published a blog post about the APT Evasive Panda, which was using adversary in the middle, mainly in China. And then in 2024, the amazing people at Volexity uncover an implant in the compromised infrastructure of an internet service provider. And the implant was intercepting traffic from a targeted network and sending it to malicious servers where the updates were hijacked. And now finally, I can talk to you about PlushDaemon. PlushDaemon has been active since at least 2019, performing cyber espionage operations against individuals and entities in China, Taiwan, Hong Kong, South Korea, the United States, New Zealand, and of course, Japan. In some cases, we identified companies in the manufacturing and engineering sector, and of course, the VPN service provider company of which I will talk today. In the case of individuals, the PlushDaemon targeted academics, software developers, and interestingly, most victims were users of VPN software. While we could not identify the majority of the targeted organizations, we noticed an emerging pattern. We suspect that they targeted the IT departments of these organizations. In several cases, they were also targeting developers. For its initial access, the primary technique is to compromise users by hijacking the software updates. And besides the supply chain compromise, we also know at least of one case in which they targeted a Taiwanese organization and exploited an unidentified vulnerability in an Apache server. The PlushDaemon toolset includes the slow stepper implant for Windows and Android. And today I will focus on the Windows version. and also the little daemon downloader, of which I will talk about in the final part of the technical section. Finally, at ESET, we attribute PlushDaemon as a China-aligned APT. So let's talk about the supply chain compromise of IPNE. IPNE is a VPN service provided by a South Korean company known as Monetcom. The service is not only for users who want to navigate with a South Korean IP address, but also Monetcom offers some corporate solutions. We can only speculate that perhaps the attackers wanted to compromise VPN users in China, or they were looking to compromise the corporate customers of Monetcom, or maybe both. We contacted Monetcom in October, and they removed the Trojanized installer from the website on the next day. In South Korea, we observed the largest cluster of victims, particularly in the network of an engineering and manufacturing company. We detected 2 other cases, one in Japan and one in China. It was actually the case of the Japanese user, our first detection of the Trojanized installer, and that happened in November 2023. So IPNE supply chain was compromised for almost a year before we noticed the large cluster of detections in South Korea. What we observed in the telemetry is that the users downloaded from the legitimate website of IPNE a zip archive that contained the Trojanized installer. The only place where we could find that exact download link is in a button in the website. So we believe most victims downloaded the archive by navigating the website and not via updates. When the installer is run, it looks quite normal, and when the installation is finished, IPNE software is launched. So if the installer is not detected by an anti-malware solution, the user will not suspect anything. However, in the background, the installer had written on disk the legitimate files from the software, but also the malicious DLL and a series of package files that contain more malicious components inside. The installer loads the malicious DLL named automessage. And automessage decrypts one of the package files that contains the installer component of slowstepper, and it decrypts an embedded shellcode stored inside of automessage. Then it resolves the address of the exit process API and patches the first bytes with a jump instruction to the shellcode. And then it returns execution to the installer. When the installer has finished, it will call exit process, and the execution will be redirected to the shellcode that will load the installer component in memory and execute it. Interestingly, this is the same technique used by NSPX30 implant from Blackwood, but the code in automessage is more polished and efficient. This was not documented publicly until 2024, as far as we know. So maybe the developers were already familiar with the NSPX30. We don't know. The installer extracts more components from one of the package files, and the package files are in reality encrypted archives with a custom format. Each archive contains multiple files, and each package can contain multiple archives. Unfortunately, the installation process is quite difficult to explain step by step, because it involves the renaming of files on disk, moving the files to other locations, and renaming them again. And you will be extremely bored by the end of it. So I will simplify it. In the end, the installer will execute a component named scvcghost.exe that monitors if the process that the host, the slow stepper backdoor is running, and if it's not, it is executed. The other big purpose of this component is to establish per-system entries in the registry. With the loading chain finished, we can now talk about the backdoor. We believe that the backdoor was originally developed around 2018, since the oldest known version of the backdoor that we detected in our telemetry was compiled on January 2019. The light or smaller version of the backdoor was used in the supply chain compromise, while the most complete version of the backdoor we have only observed in attacks via hijacked updates. The difference between the light and the full version is basically on the functionality provided by the commands, and the last known version was compiled in 2024. Both the light and full version have access to a toolkit of around 40 tools written in Go and C, but the vast majority are Python scripts, which interestingly contain a lot of comments from the authors, including the bug fixing notes. For example, they have dates of development, description of the script, the alias of the author, for example, Mr. Sao and XJY, who worked on the script that steals data from WeChat, and he left a nice log of bug fixes. This is very nice of them. This does not happen very often. The toolkit mainly provides tools for cyber espionage. For example, they can take full control of the machine using real VNC, collect data from a lot of browsers and steal cookies, steal data from chat applications and extract data from VPN software, record the screen and the microphone, and a lot more. The backdoor was developed in C++, and the developers use object-oriented programming in the code, particularly the code that handles the communication with the CNC and the part of the commands, which suggests that it was developed by professional developers and that the implant will be in service for a long time. Indeed, the implant has been around now for 6 years. All right. Now let's talk about some interesting features of the backdoor. After it initializes its configuration, it will try to obtain the addresses of the CNC servers. And for that, they chose to store them in DNS TXT records associated with a domain that they control. For example, this 360safe.company domain. The backdoor creates a DNS TXT record query packet and sends it to one of 3 public DNS servers, including Google and Alibaba. We have found a number of TXT records which we provide in our blog post, but for this presentation we will only decode one of them. The first 6 bytes are a marker used by the backdoor to validate that the TXT record was created by the attackers. If the marker is present, it will decode the base 64 string and decrypt the resulting binary blob using AES. The result is a list that, in this case, contains 10 entries or 10 CNC IP addresses. Each entry begins with a data type identifier. In this case, all of them are the identifier 4, which means that the next 4 bytes are a CNC IP address. The backdoor supports other types, for example, a combination of IP addresses and port, or data that is 16 bytes long that we suspect might be an IPv6 address, but we have not seen any TXT record containing such values. If this process of obtaining the DNS TXT record fails, the backdoor uses a fallback domain which it resolves using the getHostByName API, so it's very simple. The backdoor contacts the CNC server via TCP and then is ready to receive commands. Because this version of Slow Stepper is the light version, it has less capabilities than the full version. By default, it handles some very normal commands like collect information from the system, delete some files, uninstall, but then we notice something strange about the shell command. When we think of a backdoor and a shell, usually we think that the backdoor stores a reverse shell, but to our surprise, in Slow Stepper, the developers took the effort to implement their own interactive shell that is used to manage the backdoor and its toolkit. And what do we mean when we say that it's interactive? When passing the commands, the shell mode has predefined messages for when a parameter is missing for a command or there is a mistake in the parameter. In other cases, for example, the shell mode will let known the operator that the command is incompatible with the current configuration, as in the case of the restart self command. And it can also offer some advice. For example, when the operator sends a command to change the configuration, they can use the command gconfig reload to apply the changes immediately, or they will have to wait until the backdoor starts again, or they can use the command restart self. For this presentation, we chose to highlight the command called pycall, because it is used to execute a module from the toolkit. In this case, we will take as an example the Python script collect info. For the attacker, first, the attacker has to type and send the command pycall collect info via the CNC server to the Slow Stepper backdoor, which downloads a customized Python distribution from a remote repository. The remote repository is hosted in gitcode.net, a developer platform similar to GitHub, mainly used by Chinese developers. Unfortunately, the contents are no longer retrievable, and Slow Stepper and its toolkit failed to perform downloads from the repository. The account is in private mode. The custom Python distributions and the toolkit were hidden in a copy of an open source project called Café, which is originally on GitHub. There are 3 possible customized distributions that Slow Stepper chooses depending on the current operating system. And each distribution, the attackers inserted 2 files which contain keys for decrypting the toolkit modules and a Python script that launches a helper DLL to decrypt the modules. Each of the Python script modules is named with an MD5 hash. So for example, on the screen you can see that the Python script module that corresponds to collect info inside one of the folders in the Python distribution. To execute collect info, Slow Stepper executes the Python interpreter via the Windows command console. The command for the interpreter requests to load the support script named ronas.py and when run as is executed, it uses the help module that obtains the key files in the distribution and decrypts the requested script, in this case, collect info. Collect info produces a zip archive with a random name that contains 2 files with collected information. The majority of the scripts can output information for the operator. For example, the camera script will let the operator know if it failed. In this case, my test machine had no camera, so I could not take a picture of myself for the attackers. A slow stepper collects the files and reads the output message and sends them back to the CNC for the operator. In our blog post published today, you can find a complete list of the scripts and other tools used by the attackers. Finally, in this last section of the presentation, we'll share some information related to the hijacking of updates. This is a complete list of applications that we observed that had been hijacked by PlushDaemon. And as you can see, all of them are developed by Chinese companies, and some of them have millions of users worldwide. What we observed in our telemetry from a particular case in 2024 was that 2 components from the Sugo Pinyin software attempted to download the Little Demon downloader on the machine. In one case was an executable file, and in the other a DLL. The software downloaded the files from a legitimate domains from the Sugo infrastructure, but the IP address to which the domains were resolved in the victim machine is a little bit strange. The server had no HTTP services, and when we checked passive DNS records, we found that there were no associations to any Sugo domains. Only in our telemetry we have seen this. This is something that had not happened in cases with APTs like Blackwood or Luoyu, because they don't redirect the traffic, but they reply directly to the update request. Some days passed, and in the same machine we detected new requests sent to Sugo domains with that IP address, leading us to believe that the attackers were still ongoing, but did not result in a new attempt to download the Little Demon to the machine. This makes us suspect that the PlushDaemon hijacking uses DNS poisoning to redirect traffic to malicious servers where the hijacking occurs. Additionally, the Little Demon downloader sends HTTP GET requests to 2 legitimate domains, one from Sugo and one from Baidu, and one IP address from a server located in China that exposes no services. Little Demon expects to receive a shellcode that it decrypts and executes, which install the slow stepper in the machine. Finally, we reached the conclusion of this presentation. And to summarize, PlushDaemon has been active since at least 2019 and is a China-aligned APT. The threat actor is well-resourced with access to a complex implants with an extensive toolkit, and also have access to code signing certificates. PlushDaemon has capabilities for traffic interception to perform attacks such as DNS poisoning and the hijacking of updates. And finally, PlushDaemon does not shy away from performing riskier operations, such as the supply chain attack and compromise, where the risk of being discovered is very high, which also leads to the risk of the tools now being detected. You can check our blog post for more details, which should have been published today. And I would like to thank you all for your attention and for your time.